So thanks for joining. I understand it's after the lunchtime and many of us feel lazy. This is something similar that we did last night. We went out for a dinner. We came in, practiced a lot. We were in the same situation. Okay. So talking about this, we are from Zomato, which is called Eternal now. We are a group of businesses running at huge scale. And talking about scale, this is our journey to adopting ECS, which is Elastic ECS, which is you can understand it as an alternative or a container orchestrator built by AWS and running and adopting all these pod instances. Nearly all of our instances on production environment are working on Spot. So this is a journey from total chaos in the start to a total controlled situation right now. I'll take a brief moment here to introduce myself. So I am Gaurav. I'm alum of IIT Delhi. I have been associated with Eternal for the past 1 year. And
yeah, hi. My name is Sudip, and I'm an alumni of IIT Kharagpur. Been there in Zomato for the last 3 years. We both work at the SREday team, where we run the entire Zomato infrastructure. So Zomato means Zomato Zomato Hyperpure and the whole Eternal business infrastructure at scale. We get microservices, looks for the reliability, serviceability, everything. Over to you, Gaurav.
Yeah, thanks, Ved. Moving on to what this particular flow is going to look like. The very first thing is we run one of India's largest ECS feed. And we'll describe what the early architecture looked like and why we chose to change it, what broke it. We describe our journey to adopting Spot instances with the help of a third-party manager called Spot.io, and later on adopting ECS totally in our services. We felt a need of building our own orchestrator to manage these Spot instances because of some issues that we'll discuss later. And while making this orchestrator of our own, we hit, of course, the famous AWS limits. And secondly, we had some other issues which came in and we built around them. It's SRE day. We can't go without talking about monitoring and observability. So yeah, that's a bit off there as well. And at the end, we'll give you some key takeaways and the future plans we hold. Okay, so talking about the scale, we have about 15,000 plus tasks that we run. Tasks are nothing but pods that you'll call in a Kubernetes world. We have 40 plus ECS clusters, which are hosting about 500 microservices. This is in exclusion to some of our businesses. This is majorly Zomato, Blinkit, and Hyperpure. Rest are excluded from this. All of this is running in about 20 plus AWS accounts. So the scale is real. Talking about the Eternal journey started in 2008 when we had a very basic monolith application, which was just hosting food menus, etc. In 2015, we actually entered the online ordering business. When we entered this, things started changing. It was a monolith back in 2015, but we were growing every month, every week, in fact. And in 2018, we soon realized that the monolith architecture is not something that we can go forward with. We started creating our first microservice. And we started adopting Spot instances at this time with the help of a third-party manager. In 2019, we started complete adoption of service architecture, and we adopted ECS to host these services as well. Because, of course, the scale is about 500 microservices that we run. And in 2021, as in when we saw we were growing, we had some issues with Spot.io, we built our own orchestrator. For those of you who are not familiar with ECS, we'll be using some terminology here. I'll just clear it off very simply. ECS is, first of all, a container orchestrator provided by AWS. That's that easy to think of. In the world of Kubernetes, the basic unit is pod. Here we call it a task. The pod spec translates to a task definition. The nodes or the instances are simply called container instances in this world. The concept of microservice, which is taken with replica set and deployments, it's called the ECS service, simply. Virtual namespacing, etc. is managed by the ECS cluster, as is done by namespace there. The node groups, that is a group of nodes that you have, it's actually depicted by an auto-scaling group, or we'll refer it as ASG. And what Carpenter does, that is scaling up and down the resources, it's done by two things in this side of ECS. One thing is called capacity provider, and above auto-scaling. So the combination of these two will help you understand how auto-scaling works. We'll come to that later. First of all, what is Amazon EC2? You all know. I'm sure everyone of us has used it. I'll not take much time on describing what they are. What I want you to focus here is to understand what a on-demand and what a Spot instance actually is. So there's a lot of fuss around Spot instances, right? The on-demand instances are something that you run 24 hours, you keep it with yourself. It's available whenever you want, you can just ask them to go back. So that is a permanent resource that you take from EC2, and they're very reliable, of course. Coming to the downside, they're really expensive. On the other hand, spot instances are the instances which are actually not being booked by anyone, but you can get it at a bidding price. That bidding is dynamic and is managed by AWS. But that being said, they are quite cheap. You get approximately 60 to 80% discount on your compute. It comes at a cost. What is the cost? They can be reclaimed at any time, as Ram was saying earlier. And this seems to be a big pain point, right? And you get a 2-minute notice to act upon it. Coming to generic use cases that people would be using, most of organizations I have seen are using OD. They're burning a lot of money here, but it's an architectural choice. That being said, why are these preferred? They are good for long-lived jobs and stateful microservices. Stateful in a sense, for example, you can think of a database or a cache. They are stateful. So if you want to run those, you should take up OD or on-demand instances. Whereas spot instances are usually preferred for short-lived tasks. So if your tasks are short-lived, you will probably have a 2 spot instance available. And our CI/CD pipeline is completely being run on that. I would like you to share that this description of CI/CD is going on in the other hall. You can take it, look at it after this day is over. When is it preferred? It's preferred in a stateless microservice architecture. You can always run stateful as well, but you need to keep some nuances to cater to, which we'll cover later in the slides. So how is EC2 and ECS working together to perform the orchestration? So if you see here, the group of tasks correspond to a service. These services are emitting continuous metrics here on CloudWatch. So the metrics can be CPU, mem, we have taken this example, based upon which you specify some auto-scaling policy. Once the auto-scaling policy evaluates if you want to add or remove tasks here. So for example, in this case, we want to add 4 tasks. We send the request to, this is sent to the ECS CP, where it gets scheduled, and it tries to place these tasks on the existing instance pool. But let's say, so there are enough resources in the EC2 instance pool. You go ahead, place it. Good enough. Let's say there are not. Here comes the concept of a capacity provider. It's listening to the requests that are coming from the control plane of ECS. And secondly, it's also looking into the metrics of the ECS instance pool, based upon which it will add or remove instances. How will it add or remove? It will talk to the auto-scaling group. Yeah, that's it. Over to our spot expert, Sudip.
Yeah, thanks Gaurav for nicely introducing us with the ECS and EC2 and stitching the correlation between ECS and EKS. Now let's look at what actually the spot instance and what we are talking about this spot instance challenge, right? As earlier mentioned, also we can't run our microservices, spot we rely on it. What is the challenges, right? As Gaurav mentioned that spot instance come a cheaper rate, 60 to 80% because they are spared instance of AWS, but with the cost that they can be reclaimed at 2 minutes. And they'll be giving you a notice before taking it. So what are these notices are? So AWS give you 2 kind of notices. One is called relevance recommendation, second is called interruption. So relevance recommendation is a soft notices. So AWS try to predict one instance which are at a limited risk of being interrupted. So if they can predict, they will try to take it down and launch a new instance on a proactive manner. What do you mean by proactive? So they first launch an instance, set the instance in a running state, and they will take it down. But the spot instance interruption, that's a very critical notice. When you get it, you will get only 2 minute time. That's it. Then, and also in this case, AWS launches another replacement for you, but that's a best effort. What do you mean by best effort? That they can launch, but there might be some delay, even they might not. If you wanted to build some system around it, how you can gather those information and will be creating a solution. So for this case, they give different solutions. One is IMDS and second is event bridge. We go with the event bridge way. So event bridge is nothing but a serverless service given by AWS where any producer can send some events and then you can write some rules there. You can set a second thing and then you can write from the rules, you can filter those events and write your own consumers and work around it. This is one of the pictures that the spot interruption events actually coming and you can look at it. Now, what is it? So basically, what is the gist here? So spot instance, they're cheaper, but they can be reclaimed in 2 minutes. So what are the things that if you wanted to run any solution, what are the things that you need to look around, right? So as the instance will be terminated within 2 minutes, so you need to add some mechanism where you can gracefully shut down the affected task running on those instances. Second thing, that you need to find a replacement where you can shift the working loads in the interrupted instance and shift them in the available resources. So this is very critical. So if you are running any microservices, your microservices application startup time or when you are launching some instance, those startup times should be well under 2 minutes. Else there might be interruptions. Now, I think Gaurav mentioned already earlier that back in 2018-19, we used to use Spot.io. So it's a third-party solution which used to manage the Spot instance pool for us. But as we actually proceed next, basically in the COVID time, when we're getting enough growth, we see some of the issues that are actually coming on. And then we decided we wanted to create our own orchestration service, which is called Compute Controller. And I'll discuss in the next slide what are the challenges that we got while managing those Spot instances in the Spot.io. So Spot.io, as I mentioned earlier, is a third-party solution. It's try to predict the Spot interruption well before it actually happens. Sometimes the prediction algorithm can detect 15 minutes earlier. So they launch one replacement for you and try to shift the load. And if they fail to launch a Spot available instance, what they used to do, they used to launch on-demand instances. That would be costly, but that's a fallback mechanism there. Now, what are the issues that actually face? So in 2020-21, in the COVID time, we were getting rapid growth. Our infrastructure also increasing, but the issue that we were getting is that Spot.io was not able to scale up our infrastructure at critical times. Second thing, that the fallback mechanism was very slow. They used to take hours of time to fall back the on-demand instance from on-demand to Spot instances. So we're also bleeding money there. And again, we're giving sub 20% commission on each and every saving. So we're giving them money, but our infra was not reliable. Sometimes we used to get interruption. So that was the time that motivates us to write our own orchestration service. So let's look at the high-level overview of our orchestration service. So as mentioned by earlier Gaurav, that we run 20 plus AWS account, right? So even if we think about creating one solution and then deploying that particular solution in each and every account, that would add operational challenges, right? So we also don't do it that way. What we do is that we listen all the critical events via event bridge to a centralized AWS account where we run our solution. So this is how the flow looks like. So when we get all the information, we actually extract critical information from those events, then filter it out with a critical and non-critical data, and then we run our Compute Controller microservices. So this Compute Controller microservices listen these events and take action upon it. And before taking action, we also store the data in an OpenSearch database. It's a very useful database and come handy in our day-to-day life. Talking about the actions, what are the actions it actually take? As I mentioned earlier, that when we wanted to run our production workload in a Spot instance, I mentioned that you need to solve two problems, right? Gracefully shut down, and second is that you find a replacement. It is actually exactly the same thing. For graceful shutdown, it actually do the stop task API call at certain point of time in the Spot interruption lifecycle, and then whenever required, it add the capacity, increases compute capacity of all the auto-scaling groups. I will come to the later how we are doing it. Now, so this is, I will take little bit time that how a Spot instance lifecycle happen on the ECS control plane side. So whenever an instance got Spot interruption, ECS on behalf of them also do something. On the container instance side, they add the instance in a draining state. So what do you mean by draining state? If an instance in a draining state, that means that they will try to evict all the running instance one by one, given some condition. Second, if some of the ECS task has load balancer associated it, so control plane will send some event to the load balancers to start the deregistration delay. Deregistration delay is a mechanism where load balancer try to delete those IP from the target group so that no new requests come to the affected instance, because those instances are going to be terminated anyway, right? We don't want any new requests to be served. And third thing, in the task level, you need to handle this system. We handle it in our way. Now, I will take a deeper look at how the Spot instance lifecycle happen when we introduce the Compute Controller. So, as I mentioned earlier, that instance, whenever the Spot interruption happen, the instance has been put in a draining state by the AWS itself. So let's check T is equal to 0, the instance has been set in a draining state. Now around T70 to T80, we trigger the stop task API call from the compute controller, which will do the graceful shutdown. Now, if you see that there is a 70-second gap, what we are doing in the 70 second. So in the 70 second, the control plane cordons the instance. What do you mean by cordoning an instance? It means that no new, the instance is not schedulable. So that means that you can't place another ECS task in those particular EC2 instance. So whatever the ECS tasks will be running on this instance, whatever the microservice you are running at that particular moment, they will be running only. Second thing it do that is putting the instance in a draining state. That means that it will start affecting the instance. Now let's look how a draining instance looks like. So for example, the red color box, that's the EC2 instance. There are 4 ECS tasks are running, or you can think about their microservices. I will take your questions later after. So what the ECS control plane do is that they took up any instance randomly. They actually evaluate with the scaling policy that we actually mention in the ECS service, and they find some available resources. So if you see in the right hand side, we find a green instance where only 2 microservices running, so there are enough spaces are there. Now what we will do is that it try to place the instance here. If the instance is already running, they will evict the previous instance. And this is called eviction, and it run on the background. So the 70-second time is being utilized here. Also in that particular time, we also add capacity. So when you add a EC2 instance, it will take some time to boot up. So basically becoming ready, so the new ECS task will take place. That will take around 20 seconds. So we give enough headroom for those things to be happen in the background. So between 70 to 80 we trigger the stop task API call. So we are assuming the last end. So 80 around 110 seconds. So all the tasks will be gracefully shut down. Why it is? Because when we put a sick term event, we put a 30-second delay sick kill. So sick kill means your instance will be gone. And 120 if the interprocess doesn't complete it, EC2 will automatically take the task. So automatically again another sick kill we will get. So this is the overall solution actually that looks like. Now it's a very happy case, right? We have solved the problem of spot interruption. But I don't think we also face some challenges. Now, as I mentioned earlier, we are doing some API calls, right? Now, talking about API calls and they will not get rate limited, it will never happen, right? We also face some of the rate limits, and these are some of the examples of one of our critical API calls. What are the API rate limit that we get, and we create a solution around it. So I mentioned a few of the API calls. And if you know that in AWS, you can increase the quota of the API calls, right? So initially also we used to do increasing the quota. Then one day we found out that we can't increase the quota anymore because we already reached the global limit. Because at Eternal, we actually operate at a huge scale that we mentioned earlier, right? There are so many microservices running, and we also hit the limit of the ECS cluster, ECS service. So we can't increase the global limit. So we have to create our own solution. How can I do? There comes actually our open source cluster that we introduce you in our orchestration platform. There we use some of the metadata we already enriched. So we found out that we don't need to call some of the API calls to directly use those information from the metadata and do it ourselves. Then stop task we use jitter, and there's a silent killer in this particular overall event. There's an event bridge because we're creating those events from different event bridge. So if an event bridge throttle, you will get the request, but there will be some delay. But as I mentioned earlier, that the 2-minute window is very critical. So if you are getting some events with some delay, maybe 5 seconds, 10 seconds, your infrastructure might get terminated ungracefully. Yeah, so talking about challenges, what is the only one?
Okay, so when I joined in, everything was looking very good until something we call it mass spot interruptions came in. So for example, just imagine, you know what interruptions are. Spot interruptions come to your cluster again, and it's at the scale that your 40% of compute servers are going to die, and that's going to die in 2 minutes. That is something that happened at our organization. And you can see this message not so early ago, approximately 1.5 years ago, when we were having a lot of business impact because of this issue. So we rectified, and what the issue was, we call it the slow start problem. So the issue is very simple in that sense. So you know that your instance is about to die, the containers are about to die. You have a 2-minute window. In that 2-minute window, you need to get an instance up, and you need to place your tasks over it, and they should be up and healthy, right? So this seems to be very easy, but if you try it on your own as well, you'll probably never end up doing it less than 3 minutes or 4 minutes. And that was becoming an issue, which meant your service was unavailable at that time, and this recovery was very slow. The business impact was real. So coming to how we solved it, the very first thing that we want to mention is we went inside the instance and understood how much time is it taking to get up and ready. So it was taking around 80 seconds. We went inside the container and inside the instance and saw that the containers are being pulled in tens of seconds, but they are coming up healthy only after a minute after that. Why? So the issue is that on Bootstrap, the IOPS consumption are at peak and they are always getting throttled, any number you take. So why is that? Because there are a lot of security scans that AWS is doing on their end to ensure that the infra is good. Secondly, there are other things that you will be doing on your own as well. So what did we do? We simply just increased the IOPS to a significant number here. After increasing the IOPS, seems to be very simple, right? But we gained about a minute from here. 80 seconds went down to only 20. So out of the 2-minute window, we are down by 1, okay? Now, the second thing is, once the instance is ready, you need to get your containers up ready, right? So for this, you are pulling these images either from a Docker registry or you're pulling these images from ECR. That's not a good approach. There are always limits to what they can actually throughput on. There are API limits on that. So the best way to fight with this is, if your images are very large and they're getting time to being downloaded, just keep them inside the AMI itself, pre-bake them. Move all the common Docker layers that are among all these services to the AMI itself, so that it doesn't pull it. It will automatically fetch it from there. This optimization resulted in a reduction of 55 seconds again. So combined, we have 20 plus 5, 25-second window for now. But the last step. So we'll give it to our developers and architecture reviewers at Eternal. It's now great mandate to keep our startup times very low. So we have introduced lazy loading wherever we can, and if downloading GBs of data, we pre-bake inside the AMI itself. So the number is now 25 seconds, and this is, I think, one of the examples that we have shown, which has 23 seconds or even less later on. Okay, so was it the only issue? No, it was not. So the issue was that we are actually using a mixed instance pool. So the instances that we spawn are not of one capacity, because spot instances, you need to have a good pool of choices to take from so that the spot availability or score is good. So in this case, we actually have instances which match this structure. So we have anything from 64 vCPUs to a 16 vCPU machine. The memory can be 32 to upper low bound. So imagine one of the ASG or the node groups in the Kubernetes world. You are having a 64 vCPU instance and a spot interruption occurs. So now when the spot interruption occurs, the 16 vCPU instance comes in, because you don't have control on what instance are you going to get, because it's a mixed instance policy that you've defined. Now, this is a problem, right? You are already 48 vCPUs in deficit, and this can happen at scale. Once this happens at scale, there are issues with it. How did we solve it? The compute controller listens to all the events coming from all the sister accounts, and it, on a regular basis, fetches the relevant information on getting what the deficit is. By deficit is similarly what I explained earlier. So if the deficit is greater than 0, based upon the most common EC2 size that we get, we spawn corresponding number of instances and request ASG to do it. And this is done after every T seconds. Okay, are we done at any case?
I don't think so. So at Eternal, there's a saying that we're always 1% done. So we never stop, and wherever possible, we try to do more and try to put the system, try to play with the system and try more optimization. So here as well is that when even the system is working fine, we are looking for more optimization, and when we're going through the services, we find some good observation. So before going to the observation, let me introduce you something called ECS capacity provider. I think Gaurav already introduced. It's actually scale up and scale down the auto scaling groups, right? Now, so there's something called headroom. So for example, headroom is like a spare instances that we keep so that we can handle busty traffics or the spot instances, right? So why it is required? For example, there are 100 instances running and 95. So my capacity provider threshold is 95%. That means that 5 instances will be running without free. They are actually available at any time. That being said, how capacity provider actually scale up? So if I put so they actually create 2 kind of LM. So one is called LM high and another LM low. And White actually tried to scale up the auto-scaling group, right, the worker node pool. So they actually put the threshold 95 for evaluating their evaluation, whereas for scaling down, it's take for 85%. That means that if for 100 instance, all the 95 instances are occupied, then they will trigger the alarm that we need to scale up. Whereas while scaling down, there are only 15 instances free, right? So for scale up, they look for a higher threshold. For scaling down, they look for a lower threshold. And the evaluation period is 1 minute for scaling up, while scaling down is 15 minutes. So what is the result that when you scale up the instance, it will be very rapid, whereas while scaling down, the termination process will be slow. So this was one of the constants that actually shown to you. Now, if you see the Zomato traffic pattern, so you will see that from night 10 p.m. to morning 5 a.m., we actually steadily decreasing. Our traffic pattern is actually decreasing, right? And the limits that I talked to you, right, 15 minutes, everything are controlled by AWS and we can't modify it. So what is the solution? So as our traffic pattern, that there will not be any bursty traffic that is coming, right? So what we do is that at night time, we move the capacity provided reservation to 100%. So we remove those spare instances, so we don't require it. Second, doing those, so there's another interesting observation that if we put the limit at 100%, now AWS doesn't decrease the lower limit. It will evaluate with respect to 100%. So further scaling down the process very faster. Third thing, we don't stop there. We also run our own algorithm, try to find out that what are the instances that have been least used. So we drain those instances and the results is in front of you. So there is a huge cost savings after having all those solutions. Now,
Okay, so this is a part of the story, talking about the money that we actually save, right? So moving on. So this is these three shapes constitute to about 90% of available instances in our region. So we have compared the OD price to the spot price and the amount that we save. So usually in this case, it's 67 to 70%. But being a little conservative here, and as spot prices vary, we are saving about 65% compute power every day, which translates to about millions of dollars in a year. So that's the story. At the end, monitoring and observability. At Eternal, we deploy our monitoring stack is based upon three basic things, which is Victoria Metrics. It's an alternative to Prometheus. It's a very scalable system. I think you can also explore that. Secondly, we use Grafana and we use Amazon CloudWatch for our particular service in this case. And what do we monitor? We look at all the limits, as Sudip mentioned. We look at all the events created by the compute controller, the spot interruption rebalance metrics, the infrastructure that we are taking for granted, we also monitor that. For example, in this case, the SQS and the OpenSearch. There are proper alerting and monitoring on that. Can you go back? I just wanted to cover that OpenSearch, which we mentioned earlier. Why is it used? So there are multiple issues of tasks being throttled at some kind of an instance, and it has happened at a scale with us. So with OpenSearch, what we can do is we can find where that task was actually placed, at what time, and what kind of a machine that was. So for particular services, we get to know when to not actually, what kind of instances to not keep in that pool for that service. That brings another optimization. So this is one example of monitoring and the thing I was talking about. So the vCPU deficit here, you had a spike here. The compute controller actually calculated the spike, got the information. And at the end, compute controller launched instances corresponding to the deficit, saving us all. So yeah, at Eternal, we are always 1% done. This is a legit coffee mug that we have in our space. And that being said, we hold some future plans. The future plans are, first of all, we now have a lot of data over 4 to 5 years, and we are trying to develop a predictive algorithm on when spot interruptions are going to happen. If that works out and the metrics are good, we'll integrate that thing as well. The second problem, if you notice here, is this is the average CPU that is being used by a service, but this is one of the tasks which has lower CPU limits being reached. This is another which has a higher one. Why does it happen? As I said, some of the instances are better for some kind of workloads, right? So as we are using a mixed instance pool, the tasks are placed at multiple instances, because of which the metrics are a little flawed. And what do we want to do over here is, we want to have a weighted distribution on each task so that each instance is actually used to its 100% capacity. The last is to open source this piece of code for you so that everyone can actually enjoy spot prices and not slap anyone on the face when they talk about it. Okay, before we jump into the questions, we are always hiring, and we're hiring especially for SRE. If you feel like, you can catch us after the event, or you can drop us an email at these emails.
Yeah,
Open to
open
questions
to
now.
questions now.
Yeah.